A simply supported beam is carrying the distributed and concentrated load shown. So knowing the allowable normal stress for the grade of steel that we're going to use is 160 megapascals, we need to select the wide flange shape that should be used. At the end of this problem, we have a table with a bunch of different wide flanged beams on it. And in fact, the table is going to be the shape versus the section modulus. So what we're going to do is we're going to look at the entire beam. We need to determine the reactions at A and D. We have to figure out what the shear diagram through the entire beam is. And why do we need to do that? Because we're going to use that to calculate where the maximum moment is. Because our equation, the maximum moment is going, the maximum stress will occur at the maximum moment. And then we're going to have to find out what my section modulus is. Now, one thing to note, the picture I took this book from, it's not 20 kilonewtons, it's 20 kilonewtons per meter, because it is a distributed load. So the first thing I want to do is I need to figure out what the reaction forces are. So what we're going to do is we're going to sum the moments about point A, and we'll say counterclockwise is positive, and those moments are going to have to equal out to be 0. And so what we're going to have is we've got that force at D, we'll just call D, and it's 5 meters out, going in a counterclockwise direction. Now, I have that, let's go back to the last one here for a second, 20 kilonewtons per meter over 3 meters, which means its concentrated load is a 60 kilonewton load at 1.5 meters. It's an easy box load, so we know the centroid's right in the middle. That one's easy enough to do. And so now if we put that one in, we've got a 60 kilonewton load, and it's 1.5 meters from point A. That's going in a clockwise direction, so that'll be negative. And then we also have that 50 kilonewton concentrated force. It is 4 meters from point A. It is going in a clockwise direction. So that is also going to be a negative force. So if I go and I solve this for D, my force at D is going to be 58 kilonewtons. Okay, now we can, couple different ways that we could solve for A. If we look at it, it's a pin joint, so there's going to be an AX and an AY. So if I look at AX, well, there are no other forces in the X direction, so that's going to tell me that AX is going to be 0. To find AY, what we're going to do is we're going to take the sum of the forces in the Y direction, have to equal to 0. And we're going to say downward is positive. And so what do we have? If I sit there and I look at it, that's going to tell me that, one quick note here, we're going to draw AY as going up, and that's going to be important for our signs. So what we have is we have AY working in the negative direction. We have 60 kilonewtons working in the positive direction. I'm just working my way down the beam. We have 50 kilonewtons in the positive direction, and then we have 58 kilonewtons in the negative direction. So if I go and I solve that out, AY is 52 kilonewtons. And it's positive, so that means we've picked it going in the correct direction. So there are a couple different ways to do this next part, which is the shear diagram. I'm just going to go through the full-blown thing that we've been doing and using the equations to get us a little practice for the equation of the elastic curve. So I have my force at A, I have my force at D, I'm going to have a concentrated force here at point C. Now, and I have between A and B, I have my distributed load. And so this was 20 kilonewtons per meter, and this was 50 kilonewtons. Okay, now I only need to know the shear. Now I could do the moment diagram also, but I know the max bending moment is going to occur when shear is 0. And so for this problem, all I'll really need to do then is to calculate out the shear force, the shear diagram, find out where it crosses the x-axis, and then I know that that is where my maximum value of the shear moment is going to be. So I'm making it a little bit easier on myself. So I'm just going to draw my my bars for the V. Now I'm going to identify every place that a load comes on or comes off. And so the distributed load turns off there. I know that my concentrated load is there. And so as I look at it, I've got 3 different zones. So I'll have 3 different free body diagrams to draw. So I have the first one here. I have that force of A. And I will have a shear and a moment internally. And then I'm going to have my concentrated load. And so what's that going to be? Well, that's W, which is my intensity, times x over 2. Because if this is x to wherever we're making the cut, this is going to be x over 2 to there. Okay, our second one, what do we have? Well, the second one, we are beyond the concentrated load, the distributed load. So we can just replace the entire thing with a concentrated load because it is not going to change. And so that's W times X, so 20 kilonewton meters times 3. Oh, actually, sorry, let's change that. The intensity is Wx. This is still x over 2. And so we'll just call this the 20 kilonewton meters times 3, so, or just the 60 kilonewtons. So that's our concentrated load. And this is all before we hit the next one, so shear moment. And we still have our force at A. And then the last one is past that shear moment, past that last concentrated load before we get to point D. So we'll have 50 kilonewtons here, and then we'll have 60 kilonewtons here. Shear moment. As I said, we're going to ignore the moments, just work on the shears. But so, zone 1, free body diagram 1, all the way until right before the load ends. Zone 2, free body diagram 2. Zone 3, free body diagram 3. And so for each of these, all we're going to do is we're going to calculate out what the shear force, shear equation is. Okay, so as we look at these, we're just going to, since we're not going to be worrying about moments, sum of the forces in the y direction is going to be 0. So in this first case here, we have A, and AY is 52 kilonewtons. We have the shear force working, that's a negative because it's going up, plus the shear force. And then we have the concentrated load pushing down. So this is a distributed load all the way through here. So our concentrated load is going to be the intensity, which is 20 kilonewtons per meter, times the amount, the distance. And this is over x. Because as we're going along, we're looking at each little sliver as we go along. We need to have an equation that's going to give us everything from point A to point B, and it's going to be changing from point A to point B because we keep adding on more distributed load. And so if we start moving this stuff around, what we're going to end up with is we want to move V to the other side to isolate it because we're calculating it as a function of V. 52 kilonewtons minus 20 kilonewtons per meter times x. So that's our equation. And so what does this give us? This is a negative decaying line. And so we've got point A and point B. So let's see, at x equals 0, if we go and solve that and drop in 0 for x, our shear force is 52 kilonewtons. So that means we're going to start right up here at 52 kilonewtons. And as we go along, point B is at 3. So at x equals 3 meters, what's V? So if I plug in V here, I'm going to get negative 60 kilonewtons, 52 kilonewtons. That's going to give us negative 8 kilonewtons of force. So that's going to put us here, negative 8 kilonewtons. And this equation is a straight line, so I could just straight line between there, and there we go. Now, I've already identified a point where it crosses the x-axis, and so we can calculate out maximum moment right now, but let's just complete the diagram really quick, and then we'll come back to that. So, point 2, sum of the forces in the y direction equals 0. Downward is positive. And so what do we have? We've got our shear force plus 60 kilonewtons from our distributed load minus 58 kilonewtons from our force at A. Sorry, 52, not 58. So if I solve that, I have a constant shear force of negative 8 kilonewtons through there. So there's the next part of our shear diagram. And the last one here, downward being positive, sum of forces in the y direction equals 0. So we've got V plus 60 kilonewtons plus 50 kilonewtons minus 52 kilonewtons. And so once I move all that stuff around and solve it, I will solve V to be negative 58 kilonewtons. So this drops down here to negative 58. And that finishes off our shear diagram. Okay. So now we have our shear diagram. Now if we wanted to, we could make our moment diagram and then solve the moment equation, and then since we know that at this point right here, where it crosses, which we can figure out, we could calculate out what's the moment at that point, and then plug that back into our equation. That's one way to do it. The other way to do it is, if you remember from statics and mechanics class, if I take the area under the curve here, or the area under the curve here, because the moment is the derivation of the shear force. So if I take that area under the curve, that's also going to give me the moment. And so I can do it one of two different ways. This one's pretty easy since we got a little triangle here. It's pretty quick to figure out what the moment is. So instead of writing the moment equation, we'll just do it that way. And so what I need to know is I need to know what this x distance is from here to here. So how do I do that? Well, I go back to my equation right here. And instead of, like, from here, I want, okay, when x is equal to 0, what's v? When x is equals 3, what is v? Well, this time, what I'm going to do is I'm going to go at v equals to 0. So I'm just going to sit here and go 0 is equal to 52 kilonewtons minus 20 kilonewtons per meter times x. And I'm going to solve this for x. And so once I move this around and solve this for x, I will find that x is 2.6 meters. Okay. And this video is getting a little long, so we're going to pause here. In the next video, we're just going to finish it up.